So we're going to move on now to chapter 6. And in chapter 6, we want to start considering continuous systems. So this is like free particles and things like that. So I want to start with the Schrödinger equation. And we wrote this down for, we wrote down this equation. And this is the Schrödinger equation. But we can also consider, let's consider if we have just functions, but a function of x, for example. So suppose that the state function also depends on x. And let's just for the moment forget about time. Well, wait, I don't want to do that. We can consider time here for a second. So the state function depends on x and t, and then let's just write as a differential equation IH bar d by dt. Oops, yeah, I forgot my d by dt in here. Psi of x and t is equal to h psi of x and t, where now this capital psi of x and t is the wave function. Okay. Now we had previously found that we could represent the momentum operator p hat is minus I h bar d by dx. And so now I want to consider just a free particle here. With the Hamiltonian then being just p hat squared over 2m. So this will be minus h bar squared over 2m times the second partial derivative with respect to x. So that would just be the Hamiltonian for a free particle. There's no potential involved. Then the Schrödinger equation becomes IH bar d by dt of psi of x and t is equal to minus h bar squared over 2m times the second partial derivative with respect to Okay, so we just have a second order partial differential equation now. So now, for the moment, we have no potentials. And we want to consider solutions to this equation. We want to find solutions to this equation. So you all had math methods, is that right? So what kind of an equation does this look like to you? It's a very specific kind of equation that's in physics. What does it look like? It's a very common equation.
Okay, I saw this in partial differential equations.
Hmm?
I know I saw this in partial differential equations.
What does it look like?
You already said that one's the wave equation.
There's no wave equation.
Sorry, you said that big psi, that's big psi, right?
Yeah.
Yeah, is the wave function.
That's the wave function.
Right.
So I think, I can't remember exactly what it is, but I might be recognizing the intended pattern. So we have a derivative on one side and then a second derivative on the other side. It's like, that feels familiar to me, but I can't remember what it was called. Also been I think a year and a half maybe since math methods.
Okay, well, when you have one time derivative
Right.
and two spatial derivatives of however many space dimensions you have, it looks like the diffusion equation. Okay. So this looks,
That's what it reminds me of. It reminds me of the heat equation for PDE.
diffusion equation, which is, say, d by dt, c of x dt is equal to some kappa d2 dx squared c of x dt. Okay, that's the diffusion equation, where kappa is some diffusion constant. Okay, and so the Schrödinger equation is a diffusion equation, but it's a diffusion-like equation. It has an I equal to the square root of -1, and that changes, this little I changes everything about the character of the solutions. So what's the character of a diffusion solution? Just think of the diffusion process. What happens if this is constant? Just think of something like this being a concentration of solute or something. What happens to solute as a function of time if I put a drop of dye inside of like a cup of water?
I guess it decreases in
The density
concentration.
the concentration decreases.
Right, it just decreases, right? Goes to a uniform solution.
Right, it kind of spreads out.
Right. Okay, so that's how the diffusion equation behaves, but the Schrödinger equation behaves differently.
It's like, does the I cause it to oscillate or something?
Yeah, right. The I allows for Okay, so it's something still is diffusing here, and we'll talk about that, but it's, but at the same time, you can have wave-like solutions. So we can try, for example, let's put in a solution. Let's just some amplitude A and then e to the I, and we'll put in our wave-like solution. So this is a traveling wave solution that has t and x. Then the first partial derivative with respect to t of psi, we'll just bring down a minus I omega. So this is minus I omega, and then it's just times psi by itself again. And then if we take the second partial derivative with respect to x on psi, what happens? We'll bring down an ik on the first derivative, and then we'll bring down an ik on the second derivative, and so we'll have a minus k squared psi. And so if we write down the Schrödinger equation again, so let's look at the Schrödinger equation. So on the where we have the d by dt here, I multiply by an IH bar. So let's plug these into the Schrödinger equation. We'll have IH bar times minus I omega on the left-hand side, and then on the right-hand side we'll have minus h bar squared over 2m times the second derivative of psi here, which will be minus k squared. Okay, so we have h bar omega is equal to h bar squared k squared over 2m. And what is this? This is the Einstein relation here. This is E equals h bar omega. This is Einstein. And then this relation here, if P is equal to h bar k, then we have E equals P squared over 2m. Okay, so it satisfies it. A traveling wave solution satisfies the Schrödinger equation. And note that this equation here, note P equals h bar k. This is the de Broglie relation. We have this is h bar is h over 2 pi, and k itself is 2 pi over lambda. So this is h over lambda, and that's the de Broglie's relation. Okay, so we actually, I say if P equals h bar k, I'm going from this assumption here, so we're using de Broglie's assumption for a particle, that a particle has a wavelength, and then Einstein's relation that the energy is related to the frequency of, say, light or a vibration, for example. Okay, so the Schrödinger equation does admit a traveling wave solution, but it also has this really bizarre diffusion characteristic. So we have to, we want to understand what that is. So what does psi of x and t represent? Okay, so if let's assume, well, let's just draw a picture here. I'm going to draw the magnitude of psi squared. We know that psi can be a complex object because it's there's an I in this equation here, so. And suppose that we have some psi squared looks something like this. Then what psi squared represents is the probability of, it's actually a probability density of being between two points. So this is called the Born interpretation. Is that the probability of finding the particle between x equals a and x equals b is given by p AB, so that's the probability of finding the particle between A and B. That's the integral from A to B of the magnitude of psi. This is a function of the time in general, where we integrate over dx. Okay? So the probability density is psi of x t quantity squared. The amplitude is defined in the same way that we defined it before. You'd have an amplitude density, actually. This is the formula that is good to know, so keep that in mind. We're going to use this on several occasions here, but so in particular, if the particle is to be found somewhere, then we would have to demand that the integral from minus infinity to infinity of psi of x and t squared. Let's take out the time for a moment here. That this quantity, you could pick any time, in fact, is equal to 1. That just says the particle is somewhere. And this also means that we can expect psi of x to go to 0 for x goes to plus and minus infinity, okay? That means our particle has to be, we want our particle to be somewhere, near us if we're going to be dealing with it. So this could be the probability, this could be the wave magnitude squared of the wave function at t1 squared. And then I can have another, at some later time, the probability might just peak or something over here. This could be the magnitude of psi at t2 squared. Okay, and so so you can tell that then the probability shifts from underneath this peak here to it's mostly underneath this peak here. So that's akin to the particle moving along the x-axis.
Would the, like in that graph, would x, like would A and B, like if you were still calculating it, that would stay there, right?
Yeah, I mean, the probability there would drop, so you would, if you calculated PAB at the later time, it would be this area.
Okay, yeah, just want to make sure.
Okay, so these are important things to remember. So the wave function, the particle has to be somewhere. And so what that also means is that the wave function should go to 0 as we go to infinity. Okay, are there any questions so far? All right, let's work through some examples, but before we do, I just want to cover some integrals.
So, one thing.
Yeah.
I was writing, so I missed your explanation of that red curve there.
Okay. So if the white curve here is just the magnitude of the probability squared at time 1, then at some later time, say t2, the particle can move, for example. And so we might have the red curve as the new wave function, the magnitude squared of the wave function at that time. Okay, so if the probability of finding the particle is the area under the region of the curve,
Right.
then the greatest, so the particle had most probability to be under here, and maybe under here, but at time t2, it's more likely centered around there.
Okay.
Okay. Does that make sense?
I was kind of confused because there's T on that axis there.
Oh, sorry. Thank you. Thank you very, yeah, that's very confusing, sorry about that.
That clears it up.
Okay, good. All right, any other questions? Okay, so let's look at how we do some, we're going to be considering the area under lots of curves here. And so I want to consider things that look kind of Gaussian. So Gaussian is any function that looks like this, u minus a x squared. So if you plot it as a function of x, has an amplitude here of 1, and it just goes down, decreases exponentially towards 0, and then the width here is proportional to 1 over the length a. So 1 over a is is proportional to the width. Okay, so everybody's seen a Gaussian before? Okay, so the question is now, what is the integral that is equal to e to the minus a x squared dx from minus infinity to infinity? So how do you do that integral?
Well, I mean, derivative of the adding
I'd make a U substitution.
What are you gonna substitute?
Like some variable U is equal to, x squared. That would make it easier. And then you have, what's dx equal to half, but 1/2 U?
Yeah.
1/2 U, I mean,
Okay, you'll always end up getting back to this integral then.
darn.
So there's a trick to doing it. Anybody know the trick?
Once again, something I learned in PDE like 2 years ago.
Has anyone seen this integral done before?
I think
Yeah, lots of times.
I have, but I can't go.
Seen it done, I've done it, I just forgot how to do it.
All right, so the way to do the integral is to square it. I squared is equal to the integral over dx e to the minus ax squared. And since we're gonna do it twice, I have to change the variable to dy, e to the minus ay squared. The limits are still the same. So then this is the integral over dx and dy. This is a double integral. E to the minus a, and then we have x squared plus y squared. Okay, what's the next step?
Okay. Convert it to R.
Right. Do it. So what's the next step then? So what is this? This is, how do I convert it to R?
So would it be the integral from negative infinity to positive infinity, dr, if we're going by the way that you wrote it, e to the negative a times r?
Well, if we go to the plane, it's R
R
squared, R
right.
squared, right?
Okay, yeah.
So we've got e to the minus a r squared.
Right back where we started.
Well, almost. How do we change the measure? What does dx dy go to?
Do you take the derivative of x squared plus y squared, first with x and with y?
There's a number of ways you can derive this, but
Right.
you can also just look at a wedge.
Is it?
If that's dr,
Right.
and this is d theta. What's the area of that wedge?
Oh, it's just the area of an r, so that's, r theta? R squared theta?
No, remember this arc length here is r d
Oh, yeah.
theta, and this is r d theta times dr, so it's r dr d theta. So dx dy goes to r dr d theta,
I see.
and so we have an integral over d theta that goes from, for theta, we go from 0 to 2 pi.
Yes, that's one part of
Hmm?
it. So that I see how it would make it easier because you have one integral already solved because it goes from 0 to 2 pi. And there's no theta.
What's the r integral over?
0 to infinity.
Right, 0 to infinity, not minus infinity. Oh, I forgot my r. Okay, so that's the integral we have to do. So what's this? Well, the d theta integral, there's no thetas in here anywhere else, so I can just, there's a 2 pi that just comes out. And then we have the integral from 0 to infinity of e to the minus a r squared r dr. So in order to make this whatever exact, then I'm going to need, if the derivative up here would be minus 2a times r dr. So I need a minus 2a here, which means I need to divide by minus two a here. So then we have minus pi over a, and then e to the minus a r squared from 0 to infinity. That just gives us a minus 1, so we have pi over a. So that the integral so we have I squared is pi over a, so I is equal to the square root of pi over a. Okay? So that's an important integral to know. And let's look at some other integrals that we're going to want to look at. How do I do, let's call this J1. X e to the minus a x squared dx from minus infinity to infinity. How do I do that integral?
Would the antiderivative
Is
be,
it the U substitution?
You want to do it by parts? Do you have to do it by parts?
Yeah,
Well-
that looks a lot like just a derivative of e to the negative ax squared.
One way you can think about this integral is just to look at what the integrand is. So you've got a Gaussian here, okay? And then so I've got this function here, which is e to the minus a x squared, and this is x. So this is an even function times an odd function.
So you get an odd function. That looks something like that. So it would look kind of like this, right?
Yeah, sure, you can multiply them out. I mean, it flips it. It looks like that. Right, so this, you can just immediately, that's 0. How about the next one? How do we do that integral?
Even function. Oh, sorry. That's an even function, so it's an even function.
Okay, I mean, you can do that a number of ways. I'll show you a trick that's fast. So in general, we would like to be able to get every integral j in that has the integral of x to the n e to the minus a x squared dx. Okay, these are what these integrals are just different moments of this function, basically. So how do we do that? We can look at the first integral that we wrote down as a function of a. It's the integral over dx of e to the minus a x squared. Right? But it's a function of a, so that means I can take the derivative of this function. I can take di dA, and because I'm integrating over x, and x is not a, then I can just write this as minus x squared. I'm taking the derivative now with respect to a, of e to the minus a x squared. Okay, so this is equal to minus j2. So so J2 is equal to minus DIA dA, that's minus the derivative with respect to A of the square root of pi over A, which is easy enough. So this is the square root of pi just comes out, and then we've got the minus sign, and then we have d by dA with a to the minus a half. So this is equal to, that's 1/2 a to the minus 3/2. So this is 1/2 square root pi over a to the 3/2. Okay, so you can compute all of them just by doing that. So let's look now at let's just look at normalizing the probability distribution then of.
So for all the, so for all odd numbers, n, is the integral always 0?
Yes, because it's odd, yeah. Yeah, so n. It's 0 for n odd, and then there's a general formula for this thing here, and you just keep, you can work it out if you just do the next few derivatives. It's pretty simple. So let's look at, so let's compute the, so suppose, example here. Suppose we have some probability density that's equal to a e to the minus lambda x minus a squared. Okay, so this is shifted. When x equals a, that's when this goes to 0 and you get your maximum value. So at some a here, we have a maximum value, and that value is a. So the question here is, let's find a, capital A. So let's normalize it. How do we do that? Means if we want to normalize it, we want to just find we want the integral
To be,
rho of x from minus infinity to infinity to be 1. So that means we have a times the integral minus infinity to infinity of e to the minus lambda x minus a squared dx equals 1. So how do we do this integral where it's shifted?
is it a u substitution this time?
You could do it by u substitution.
You got one.
Hmm?
It's like, finally got
Well, what is it though?
one.
I mean, you can also just do it without writing anything down. What does it have to be?
Oh,
Oh, yeah, so it's gotta be some. So is a equal to a over pi? Does it's an interval like that always give you pi over a?
No?
Oh, pi over lambda, I mean, but.
well,
Oh, now, well, what is the integral? What's the value of this integral?
It's pi over lambda, right?
It's pi over lambda. Why is that?
Because he told us earlier.
It's the square root of pi over lambda.
Square root of pi over lambda, right?
So A is equal to the square root of lambda over pi. Okay, shifting it doesn't do anything to the area.
Yeah.
Right.
Okay, so we have that. Now let's find the first moment. Find the expectation value for x with this probability distribution. What's the integral I have to do?
You said it was the first moment. That's not J1, is it?
Yeah, I mean it is, but we have this probability distribution, so I'm not centered, it's not J1 because this is centered at 0, and ours is not centered at 0. So, but this is the integral, minus infinity to infinity of x times a e to the minus lambda x minus a squared dx.
So would it be 0 for the same symmetry reasons?
Well, consider the integrals now. You have, I've got this function that's shifted over by a, and then I've got this function, and I have to multiply them. Does it go to 0?
No,
Mm.
because it's not symmetric about the y-axis.
Right. So how do you solve this one?
Is it
It is. I knew you were wanting to do a substitution, you know.
Finally.
Now we got a substitution. Okay.
Hey, when all you guys are hammered.
No, that's hilarious though. Okay, so this you've solved by substitution because what do you want to do? You want to shift the Gaussian back to 0, and then you'll just get a linear term here in the x, right?
Right.
So here we can do that. We can let u equals x minus a. Right, so then du is just dx, a is a constant. And then x is equal to u plus a. So the expectation value then is, the limits are the same, so we're just integrating over du now, but now we have u plus a times e to the minus lambda u squared. Oops. All right. Okay, so what's the first one? What's the, so this, now I have I just have two integrals here, right? Two infinite integrals. I've got the one with the u and then the one with the a.
Right.
Right? So what's the first one?
Oh, okay.
So the first one would be 0.
Right, from symmetry.
Yeah.
Right, so that'll be 0 plus little a now times capital A.
Yeah, I guess 1 5.
Times capital A times the integral then, which is the square root of
Just go to pi over lambda.
pi over lambda. So a is the square root of lambda over pi, so this is just a. Okay, which makes perfect sense because if that's where your probability distribution is, we just asked for the first moment, which is what's the expectation value of x, and so it just gives you what you expect. Okay, and then you could ask for, the expectation value of x squared, and you could play the same game. Then you would have the integral of x squared, e to the minus lambda x minus a squared, and again, you would do the u substitution, and then you would just get a squared here, so you would square this out, and then you would have some terms that were zero by symmetry again, and then you'd actually get a u squared term. So you would have an integral like j2. Okay, so if you calculate this, and this is 1 over 2 lambda plus a squared. Okay, so that's the general picture of what the probability distribution, or what this wave function means. It's just a probability distribution. And so now that you know that, now let's go into some more of the formalism, the quantum mechanics formalism. So this was just some this is some stuff that will come in handy when we run into actual problems later, because we want to find, we want to calculate psi, the wave function itself, for different situations. You know, we want to calculate the particle in a box, for example. We'll do that, and then other potentials where we'll have particles in confined spaces, for example, or in other different potentials, and so we want to calculate these kinds of integrals to calculate the properties. So let's do some quantum mechanics now with continuous state spaces. Let's see, quantum mechanics. So we need to understand how to handle these infinite dimensional spaces, because they're not as simple to work with as the finite dimensional spaces. And so let's start with just looking at the position. When we were first considering particles in the quantum mechanics, we were considering states of particles that didn't have anything to do with their position. It was just the spin was up or down or whatnot. But we didn't talk really at all about the position of the particle. So now we want to talk about the position of the particle. And so the position can represent a state. I mean, the particle is at a particular position. Position is observable, and so it should have a state. Observable, so it has an operator, call it x hat, and a set of states. That are infinite in number. Okay, so in particular, we write down our standard equation here for an operator and a set of states that go with our Hermitian operator. We have operator, we have the state, we have the eigenvalue that the operator brings out of the state, or whenever you operate on the state, you get the eigenvalue for that eigenvector. And so this is just your standard eigenvalue equation. Okay, so now, when we were discussing, spin, we wrote equations like z plus, z minus equals 0, and z plus equals 1, to demonstrate the orthogonality. Here, we have to write things like x prime x is equal to delta x prime minus x, okay, where this is the Dirac delta function. Okay, and so these represent two different positions. You know, if x and x prime are different, then this is 0. The Dirac delta function is defined by the following properties: that the integral, if we integrate over dx, that we get 1, but the delta of x minus x prime is equal to, is 0 if x is not equal to x prime, and it's infinite if x equals x prime. Okay, that's a really strange function. That means that the Dirac delta function is just very sharply peaked at x equals 0. It just shoots up. It's this big infinite spike, and it's infinitely narrow. Okay, so it's infinitely narrow, but it has an infinite spike in such that if you integrate under it, the area is 1. What are the units of the delta function?
It has units.
It does.
Oh, right, because it has an area.
Right.
So, well, what's the y value there? The probability?
It's just a function.
Just a function.
It's not really a function, but it's a distribution.
Right, it's a distribution.
Um,
People call it a function, it's clearly a distribution.
I wouldn't say clearly. I mean, it's kind of hard to pin down the properties of this thing. You know, you have to do some serious math. But anyway, what are the units of the delta function? Well,
Is it x squared? Units of position squared?
no, I mean, the right-hand side is 1. It's unitless.
Oh, so it's inverse. Inverse x,
Yeah.
whatever x is.
Right. Good. Okay, so are we all clear on this infinite number of basis states for the position? Let's let's see here. We also wrote before for the completeness relation. Remember that completeness relation? So now we have to do the following. Now we have to integrate, so, whoops, let's break it down some. Okay, so now we have this relationship. Okay? All right, so now let's put some of this formalism to use. So suppose we have a particle in state psi. Now, this is just a general arbitrary state. I haven't told you anything. I mean, when I write it abstractly like this, it's just like writing an abstract vector. There's no coordinate system or anything associated with it. We still demand that the inner product of psi with itself equals 1. Okay? So the particle has to be somewhere. Now let's use our completeness relation. So let's call this star. Let's insert star. So I'm just going to put it right in the middle. So that would be the integral over dx from minus infinity to infinity of psi x psi. Okay, I'm just putting this relationship right in the middle of that bracket. And if we do that, then we can make a quick definition. Let's define psi of x is equal to x acting on psi, okay? So what we're taking is, we have the abstract state vector psi. We're taking the bracket with x, at a particular position x, and so that just tells us what the value of the function is at x. So it's some function. Okay? All right, so what does that mean? That means this is psi of x. What's this one over here on the left? Right. So psi x is the complex conjugate. So we have this just becomes, with our definitions, this becomes this expression here. Okay, and that's just our expression for the magnitude squared of the wave function psi of x magnitude squared equals 1. Okay, are there any questions about that? No? All right, let's see how some of the formalism works here. Let's look at this translation operator. So recall the translation operator, t hat a. And if the translation operator acts on a particular state, x, we want it to translate the state to x plus a. State vector. And then let's look at, see how, so now let's consider how does t hat a, the translation operator, act on a state vector psi. So psi itself is, again, it's a completely abstract state vector. There's no coordinates here. So if I let TA act on the state vector, I'm going to have to, probe it somehow, basically by hitting it on the left with some other x prime. Otherwise, I just won't know how it's behaving, how it's acting on that state vector. So we can just write t of a on psi. And before I do anything else, I'm just going to use my completeness relation because I know how TA acts on this, the state vectors x. So we can go ahead and put that in as integral over dx t hat of a acting on x psi. Okay. Bless you. And we know that this is a plus x, so this is the integral over dx. This is now x plus a, x psi. Okay, this is just, that's just psi of x. And now we can probe with, by coming in on the left with x prime. So that's dx over x prime, x plus a times psi of x. And now we can go back to our Dirac delta function definition and say that it's the difference of these two things. This is delta x prime minus x plus a. Okay. But what's that? I mean, this is delta of x prime minus a minus x. I can just rewrite it like that. So when I integrate this I'm integrating over dx, so I just plug in this argument goes right into the psi argument. So this is psi of x prime minus a. Okay. So you can notice something here. I can write this as x prime minus a psi. Okay, so t acting to the left gives you a minus. T acting to the right gives you a plus. Okay? Okay, and I think that's a good stopping point. Are there any